Wait, man, can you walk back and forth? We'll just test the. Oh, dear Lord. What is wrong with this computer? Someone check the screen. Check the stream on your phones. Is it lagging or is it just the computer? Give it a couple minutes. We're just checking if it's lagging. Did you hit record on the? It's black. Oh, hold on. Wait, did you hit record on the camera? Wait. Okay. It's not recording. Okay. No, I changed it. Yeah, hold on to this. So this next to the mic.
So this is the lav. Wait, should I lav this or should I just hold it?
I just hold it. I'll give you the mic after.
Oh, okay.
The
So that would be mine.
Hold on,
And then this
because
is
it's
yours.
a
Wait.
pre-show. God damn it.
Oh, okay. Yeah.
We need to like uninstall like everything on that laptop. No, it wasn't.
Wait, can I lav it like this? Will that? Yeah. I don't know how audible it will be. Maybe I need to like.
Alright, it should be working now.
It's like dragging my shirt down.
Someone get a laptop charger.
Do you have a laptop charger?
Depends. What for what? USB-C?
Yeah.
No.
Break or something.
No. Hold on.
Good adapter.
I don't think so. I have like a System 76 charger.
Oh, real? Hold on, I know what to do.
I have like a AC adapter. Do you have like a barrel jack on yours?
No, it's USB-C on this one.
Right.
We can just turn off power saving mode.
Yeah, I think.
I have one at home. It's in.
If I can get to it. Hold on, I'm having a stroke. Hold on, we're just trying to turn off battery saver mode because it's lagging.
Yeah. No worries. You're good. No stress. Hey, Auntie, check it out.
Oh my god.
You know why this happened? I got so unbelievably bored waiting for my OS architecture to go live that I painted my nails.
Okay, there we go.
Okay. I'll take the stream.
Hey? Not for the talk,
There is like
but
literally no.
I was tempted. I really was tempted.
It's black.
It's still. Hold on, no, it should be updating very soon.
Do you reckon I should put this shit on charge?
Oh, there we go. Got it.
Right,
I've
you've
got
got the stuff.
73%. Oh, sure.
Hello. Thank you for your patience. Welcome to the first talk of semester 2. Today we have Matt Young, and he'll be talking about digital chip design. And I'll give it right to him. Thank you.
Cool. Just all right. Hello, everyone, and thank you so much for joining me here today. So this is going to be my talk on digital chip design, tools and techniques. So without further ado, I'll get into it. Or will I? I will. Okay, so I first thought I'd just give a little bit of an introduction about who I am. So my name is Matt. I'm a 5th year Bachelor of Computer Science honors student. I graduated my undergraduate Bachelor of Computer Science last year. I'm also a part-time software engineer at Emesent, which is a robotics mapping company that is based out of Milton. I completed my research thesis on fault-tolerant EDA techniques for spaceflight computing. And I'm generally passionate about computer engineering, retro computing, optimization, and a bunch of other things. I'm currently in the process of applying to do a PhD next year at Macquarie University's Silicon Platforms Laboratory in Sydney. I'm a long-time UQCS lurker since about 2021, but this is my first speech. And a fun fact about me is that I also do scuba diving. So I wanted to give a little bit of context, like why do semiconductors actually matter? Well, to start out with, the semiconductor industry was worth last year alone almost $500 billion. But far more than the monetary value, chips are also increasingly becoming a geopolitical issue. Whoever can design and fabricate the best chips is increasingly becoming a global superpower. And in fact, chip design itself is essential for basically just about every industry we do. In essence, chips are sort of the fundamental technology that underpins just about everything we do in society today. But despite this, chip design actually barely exists in Australia, and it's not really taught in universities. And it's my mission to be able to change this, and that's part of what I'm trying to do as part of this talk. So I'd just like to give a bit of an agenda about what we're going to cover today. Firstly, I'm going to give you a bit of an introduction, as much as I can in a short period of time, to computer engineering, to sort of give you a bit of a background context about what we're talking about here today. Then I'm going to drill down on specifically electronic design automation techniques, like what my thesis was on. And with this, I'm hoping that you'll be able to understand understand the magic that allows us to lay out billions of transistors on chips. And then finally, I'd like to give you a bit of my opinion about how you can get involved and the sort of the challenges and processes to kickstarting your sort of career or research career in semiconductors. So without further ado, I'll start on my introduction to computer engineering. Firstly, I'd like to say that there is a lot of jargon in this industry. If you don't understand something that I'm saying, please stop me and I'll gladly clarify. There are so many acronyms and I'll be happy to explain any of it. So to start out with, the first thing to talk about is an IC, or an integrated circuit. In this presentation, we're talking about digital ICs. So analog ICs are also very common, but are significantly different, and not much that I'll talk about in the presentation today will actually apply. The caveat is that most designs are typically what's known as mixed signal, which means they contain both analog and digital components. The next thing to talk about is an ASIC, which stands for an application-specific integrated circuit. So some examples of what ASICs are NPUs, or neural processing units, that have become quite popular with the AI craze, GPUs, I'm sure you all know graphics cards, ISPs, you might not have heard of that. That's an image signal processor that will be used, for example, in cameras, display controllers, Super I/O controllers are on motherboards, disk controllers, audio codecs, video codecs, the list goes on. ASICs are everywhere. And in fact, if you can see this presentation, it's very likely that you're using many of the above. So now I'd just like to talk a little bit about what actually digital logic is. If you've done CSE 2010 or something similar, recall that digital logic is fundamentally binary, so we're talking about ones and zeros. And when we construct digital logic, we use combinatorial logic gates like AND, OR, etc., and also sequential gates like D flip-flops. At its core, every ASIC is fundamentally just these gates. There are some terms and conditions, but for the context of this presentation, we'll say that. However, it is true that in reality, everything is fundamentally analog. Digital is merely an interpretation that we apply, or we discretize voltages that we get into low and high to achieve binary 0-1 logic. But of course, the real world is never ideal, and as part of ASIC design, we have to consider that. And I'll be able to talk a little bit more about that once we get into EDA. So here's an example of a combinatorial circuit. If you've done CSE 2010, you've probably seen many of these. This is a 1-bit full adder, so you can see how it's built using the logic gates here, and then of course the truth table on the right-hand side demonstrates the function of this combinatorial circuit. This is an example then of a sequential circuit. So this is what's known as a 4-bit serial in, parallel out, or SIPO shift register. So this is going to take bits in, shift them through the D flip-flops, and then you can read out the whole 4-bit word sort of instantaneously. But we understand this. So what actually is an integrated circuit? I find it's not typically well known what actually an integrated circuit is made of. But we know that ICs consist of millions and sometimes billions nowadays of transistors that are etched onto a silicon wafer using a chemical process known as photolithography. The way the photolithography is performed, or what's called the setup, forms what we call the process node, which in turn forms the transistor size, which in the industry we refer to as gate pitch. And this is what people talk about when they talk about, say, your 4 nanometer chips or something like that. But this is actually an advertising term. There is zero correlation nowadays between what is advertised as being a 4 nanometer chip and the actual gate size of the chip. Some examples of photolithography techniques that are commonly used include deep ultraviolet lithography, or DUV, which is used for chips that are billed as being 14 nanometers and above, and also extreme ultraviolet lithography, or EUV, which is used for 7 nanometer and beyond chips. Okay. ASML, which is a company that manufactures photolithography devices, these machines can cost upwards of $100 million per device, and are honestly considered quite possibly some of the most complex machines on Earth. Now, this image is an example of what's called a wafer. And a wafer basically consists of a bunch of dies that have been etched onto a silicon platter, and each of these dies can then be taken off later and turned into a single integrated circuit. So we talked earlier about a transistor, and we know that the transistor is the fundamental component of ICs, but how does it work? So basically, it works by, at a bird's eye view, current can be conducted between the source and the drain, depending on the voltage at the gate. And this is the reason why it's called a semiconductor, because depending on the gate, the current will either flow or it will not flow. And the way that modern transistors are constructed is using, they're called complementary metal oxide semiconductor, or CMOS transistors. Now, CMOS transistors are a combination of 2 older types of transistors known as NMOS and PMOS, which are N metal oxide and P-type metal oxide semiconductor. The reason why CMOS is used nowadays is because CMOS has significantly better what's known as static power or leakage current than NMOS and PMOS transistors, and also, of course, faster switching times. What we refer to as static leakage is basically the idle power that the transistor uses when it is not switching. And the way it's cancelled out is because, of course, they're complementary. The N-type and P-type transistors effectively sort of cancel each other out and bring that leakage current much further down, which means that they're much more power efficient. And the way we actually build circuits is we combine these transistors into what's known as a standard cell. And these are, in essence, when you're designing chips, the building blocks of modern sort of ASICs. They're unique to a particular foundry and process node. They're typically delivered as part of what's known as a process design kit, usually after signing about 9 million NDAs. Rather than each company redesigning standard logic cells from scratch, like your AND or NAND or SRAM, the foundry will do it for you, which is much more efficient. And it's even more efficient for the place and route tools, and it saves a lot of designer time, and it generally makes these devices a lot easier to design and manufacture nowadays. So what does this all look like combined together? This is what's known as a die shot. So the dies that we talked about on that wafer before, this is what a single die will look like. This is on quite an old process node, and it is a 2-input NAND gate, which is about as simple as it will get. But you can see that the transistors have been etched onto this die, and this is now something that you'll find in one of those, black, like packaged chips that you might use. So another thing that you might have heard a lot is something that is known as an FPGA. The reason why FPGAs exist is because manufacturing silicon ICs is extremely expensive when you're not operating under economies of scale. They're basically, manufacturing an IC is totally uneconomic for low volume runs. But of course, people still need many of the benefits that ICs and ASICs provide. And hence the field programmable gate array allows for many of these benefits at essentially a fraction of the cost. So this is a block diagram of an FPGA. This is one of my favorites, the Lattice ICE40 from a company called Lattice Semiconductor. An FPGA can consist of up to several 100,000 what's typically known as logic cells, although the terminology can differ a little bit depending on the vendor. And these can basically be chained together to implement any sort of digital logic function, which is why they're so very flexible. The configuration, or what is known as the bit stream, is written to the FPGA's SRAM, or static random access memory, on boot, which means that they are cheap and easy to flash. Still, though, these FPGAs have worse power, performance, and area, which is a key metric that we measure in the semiconductor industry, than an actual silicon ASIC. And this is why ASICs are still designed and not everything is just done, with an FPGA. So from the previous block diagram, this is a sort of an up-close view of what Lattice actually calls their programmable logic blocks. And you can see here that it is built of a 4-input lookup table, LUT, which basically allows the logic block to approximate, or not to approximate, to actually implement any sort of logic function that can be expressed with 4 input variables. And then, of course, it is also passed into a sequential 1-bit D flip-flop. And what this means is that combined together, a single logic block can implement both a combinatorial and sequential function as part of it. So now let's talk a little bit about what electronic design automation, or EDA, is. Basically, in ye olden days, chips were mostly designed actually using pencil and paper by scratch. And this actually includes the first Intel CPUs. Transistors were manually drawn out. But that's where the term the tape out comes from. If you've ever heard people talking about taping out a chip, this is what they mean. But nowadays, ICs consist of billions of transistors, and hence, doing it manually hasn't really been an option since like the late 80s. Instead, we use electronic design automation, or CAD tools. The way these tools generally work is that they take an input language, such as Verilog, System Verilog, or VHDL, and these are known as hardware description languages, sort of the source code, if you will, of FPGAs and ICs. And in the semiconductor industry, we call these types of languages RTLs, or register transfer languages, because they model sort of the transfer of data between sequential registers. Now, these languages are actually used for both synthesis, like what is going to be put on the actual chip, as well as simulation, which is totally not confusing and has never caused any bugs ever. Anyway, both circuits and simulation test benches can be described using simple text-based constructs. It is similar to software code, but be careful. The analogy kind of breaks down because hardware and software are very different. And hence, if you try to write an HDL-like code, you probably won't get very far. But we'll go back to the analogy for a bit because EDA tools are sort of like the compilers of the semiconductor industry. What they do is take HDL code and produce for FPGAs what is known as the bit stream, that is get flashed to the FPGA and provides its configuration. Or for ASICs, they provide a photolithography mask that will be actually etched onto the silicon. And you can sort of think of like a bit stream or photolithography mask as sort of like machine code or object files in the software world. But again, be warned, the analogy is not completely true. It is true, as we'll get to later, that these tools both do parsing and sort of optimization, but ADA tools consist of many NP-complete problems all throughout, and hence ASICs can take sometimes weeks to compile. So this is an example of some System Verilog code. So the code is on the right-hand side here, and you can see that the sort of circuit schematic that it resolves into at the end. I wouldn't worry too much about trying to understand everything completely, but you can see the general gist is that over here we have what is known as a sensitivity list, which is basically saying every time this clock toggles, we want to assign the value of A into this flip-flop. And you can see, sure enough, the clock, the D flip-flop, and A is as the input. That is a sequential, that infers a sequential logic because we've said always FF or always flip-flop. And then there's also an inversion here, which comes from this not sign here, and that is the combinatorial part. So this is a general overview of how the EDA pipeline generally works to provide a little bit of context. This diagram I wrote for my thesis, and it's for FPGAs, but ASICs are very similar in general. There's two main stages, synthesis and what's called place and route, or PNR. So synthesis, basically the job is to take this high-level RTL, the system Verilog code, for example, that we talked about earlier, and turn it into a netlist, which is basically a bunch of connections. And so it's not physically based. It doesn't consider the area that this would take up in any degree. Whereas for place and route, this is where things actually become physical, and we want to take this netlist and map it to the resources that a given FPGA or a given design library for an ASIC will have. So yeah, if EDA tools are sort of like the compilers of the semiconductor industry, then UQCS is sort of like GCC and Clang. For some context, the semiconductor industry is very privatized and very expensive. Until the last decade, open source basically didn't exist. Everything is IP'd and patented to hell and back, and everything, you know, just the tools if you want to design and manufacture a chip could set you back literally more than $1 million a year. Basically, this sucks unless you're like Intel or AMD or whoever. So if you're a researcher or startup, basically good luck. Comparatively now though, UQCS is a free and open source EDA synthesis tool, which in turn is backed by Berkeley's ABC logic synthesis tool. It's high quality, research grade, and production ready, and it's managed by UQCS HQ, which is an Austrian company. When combined together with a place and route tool called NextPNR, this sort of end-to-end flow supports various lattice FPGAs like the ICE40 that I showed a diagram of earlier, and a few others. And this tool was built using very, very complicated bitstream reverse engineering by a bunch of very talented hackers. It also supports interesting formal verification flows like equivalence checking and mutation coverage, which will probably be familiar if anyone's worked with program analysis, because it all uses SAT under the hood. Now, UQCS is a key component of modern sort of open source EDA and EDA research. Another tool that we'll cover today is OpenRoad. Now, OpenRoad is an advanced open source ASIC place and route tool, and it's capable of autonomously generating basically these highly optimized photolithography masks that I talked about earlier from UQCS or any other netlist. The tool is developed by various US West Coast universities and was also partially sponsored by DARPA. And yes, even DARPA cannot afford these EDA tools. They're that expensive. The state of the art, though, is that basically at home, using entirely free and open source software, you can design and manufacture, or have manufactured, an entire chip using Skywater Technologies' 130 nanometer process node. And this is an amazing result and is only thanks to some of the many tools that are listed here, which are all open source. So if you are interested in sort of reading more about this, I would highly recommend this textbook. I don't usually recommend textbooks, and I haven't really read any myself except this one, but this is probably the only actual textbook I'd recommend buying. Majority of the information I learned from this book in particular. It is really good. So before I start the EDA section, does anyone have any questions? No? Oh. Yeah, sure. There you go. Good? Yeah, it's good. There's many places to read it if you don't want to buy it. So yeah, let's talk now about EDA. So in my opinion, EDA is sort of the arguably where the real magic of chip design happens. I mean, obviously the designers are very, very talented and it's a very difficult job, but EDA is what enables these simple text descriptions to be turned into highly, highly optimized digital circuits, sometimes with billions of transistors that operate at gigahertz speeds. So how is this possible? Well, since the two tools that I talked about are open source, we can actually use a sort of case example of UQCS and OpenRoad to learn how the magic works under the hood. So at the very top of the stage, we have parsing. Basically, a UQCS front end will read Verilog and generate an abstract syntax tree and then lowers it into an intermediate language that it calls the RTL intermediate language, or RTL-IL. As we talked about before, but just to refresh, a netlist is a lower level description of a circuit that basically combines together all the individual connections between blocks and cells. The power of UQCS is that it doesn't just ingest a particular language, it can ingest many, and people have written sort of custom front ends for it. And just a side note is that I would say Verilog is to system Verilog as C is to C++, and VHDL is kind of off in its own world. This should sort of all be relatively familiar if you've taken or will take Comp 4403. It's pretty standard sort of compiler architecture. The next stage is what's known as elaboration. So basically this works by having what's known as parsers iterate over the netlist and apply some transformation to it. So for example, we might choose to flatten module hierarchies, expand generate definitions, which are kind of like macros, turn process statements like that always FF we talked about earlier into sequential actual circuits, and do many, many other things. Again, this isn't groundbreaking stuff. It should be relatively familiar. You know, it's very similar to the way that compilers work. But now let's talk about optimization. This is where things get really interesting because we can actually perform some optimizations at the synthesis level. So what can UQCS do for us? These are a bunch of parsers that UQCS can apply, a bunch of different optimization parsers. This includes stuff like cleaning the netlist, removing unused cells, applying De Morgan's law, optimizing various expressions, merging things, reducing things, sharing logic. These are a bunch of just the optimizations that UQCS includes. We can also apply what's known as peephole optimizations, which are sort of inline micro optimizations to individual expressions. Things like changing the way a multiply is written or changing a multiply to a shift because it's cheaper. And this is a very useful type of optimization. And since UQCS is a synthesis tool, not a compiler, there are also a bunch of special optimizations that we can apply, such as identifying finite state machines and recoding them. For example, if you've done 2010, you might know binary, one hot. Sometimes they have different trade-offs, even Gray's code. And UQCS is capable of identifying the optimal coding for any given finite state machine and rewriting it. We can reduce the bit width, remove unused bits, and also insert special types of multipliers. You know, if you go into your Verilog and write, you know, C equals A times B, you have to infer the right multiplier circuit to actually insert into the schematic. And now the final stage is what's known as technology mapping, because what we have at this point is what's known as a technology independent netlist. We have, you know, our basic AND, NAND, NOT, that type of gates, but we want to lower it into a technology specific netlist, which will be useful to the actual chip foundry or specific FPGA that we're working with. And in UQCS's case, that's where this ABC tool comes in handy. So ABC will go ahead and rewrite the netlist as what's called an AND inverter graph, or AIG. This is a type of directed acyclic graph, which you'll learn about in Comp 3506, and it makes it easy to perform logic optimizations. And technology mapping will work for both combinatorial and sequential circuits. The way ABC does its optimizations is using special rewriting and cutting algorithms, and it also operates in a timing-driven manner to optimize the AIG. And you can see an example of AIG on the right-hand side here for a given sort of Boolean expression. Now, finally, the output of ABC basically gets re-imported back into UQCS, and some minor optimizations are applied. UQCS likes to do optimizations wherever it can. And now what we have is a special technology, optimized technology-specific netlist for a given ASIC PDK that we talked about, like for a particular foundry, for a particular process node, and also or a particular FPGA. So now we'll get into place and route, which is sort of my favorite section. So the place and route flow is very complex and time consuming. We do have our net lists at the moment, but they're void of like any physicality. We know what needs to be connected, but we don't know how to connect it, and we don't know how much area that will take, and how much power that might draw. And place and route can solve this for us. So this is the general overview of how the place and route flow works. The section that I've highlighted in red is the main sort of place and route flow. We start off with floor planning, then we do placement, routing, what's known as clock tree synthesis. We also do physical characterization, and then we also apply design rule checks, and finally we export the actual mask for the particular foundry. And now I'll sort of cover each of these in some more detail. So the floor plan is a global overview of how the functional units of a particular chip will actually eventually be placed. Floor planning can be done manually, which is typical, or it can actually be automated and solved using integer linear programming. OpenRoad, because OpenRoad focuses on having an autonomous end-to-end flow, it chooses the automated approach. But it is worth noting that automation is NP complete. And just in case people don't know what that means, it means that it has an exponential time complexity. So it's very complicated to solve. And hence, this is why floor planning is done manually, often by experienced design engineers. There's a lot of heuristics and just sort of design wisdom in this stage. The next stage is global placement. Basically, the goal of global placement is to generate a rough solution about where we want to place the individual blocks on the chip. We know that this might violate some constraints at the time, but the advantage of global placement is that it's going to keep an overview, a global overview of the whole netlist. Because it's so early in the design flow, the global placer doesn't have access to routing quality metrics and timing information, and this has to be sort of estimated using various techniques. Essentially, global placement is a very large, multi-dimensional, multi-objective optimization problem with very poorly defined gradients, which basically means that it is very, very, very challenging to solve. And that's why global placement is sort of my favorite part of the design pipeline. And I should hopefully be able to show you a GIF of what this looks like. So yeah, this is the algorithm that OpenRoad uses, actually solving the global placement problem for a given chip. This is a real chip. I think it's a RISC-V CPU. And yeah, you can see the way that it iteratively refines its solution and optimally places all of the blocks on the chip. So back to the presentation. After we've done global placement, we can now do detailed placement, which also ties in with what's known as legalization. Basically, we use these techniques simultaneously to finalize the layout prepared by the global placer. This can involve simple stuff like turning continuous coordinates like 1 dot something into discrete coordinates, which might sound simple, but keep in mind that even very, very minor changes can have a drastic effect on the overall power, performance, and area of the final chip. And also we need to appropriately space apart the standard cells that we talked about in the very beginning, because these have particular spacing and placing requirements that we need to consider. Basically, the goal is to take this globally placed design and try to validate it and legalize it while minimizing the impacts that we have on the overall quality of the chip. This detailed placement stage is more tractable than this sort of global placement because dynamic programming is an option, not just this NP complete integer linear programming. So now that our chip is placed, we need to move into the routing stage. Basically, we've placed all this stuff down, and now we need to know how to connect it up, and that's what the routing stage does. Like placement, there is also global routing and what's called detailed routing. The general aim of any routing algorithm is to minimize the total wire length, which will correlate well with improving the quality of the chip and increasing timing, making it faster. In the global routing stage, we basically assign loose sort of layouts to wires and allocate what's known as routing regions, which you can kind of see here, these routing regions, and then the sort of wishy-washy wires. And then in the detailed routing stage, we actually go and clean this up and apply a geometric structure to the wires. Now, this is where things get challenging again, because this is also an NP-complete problem. So you can kind of already see that we're maybe in the middle of the design pipeline at the moment, and we already have 2 NP-complete problems, which is why chips take so long to actually have manufactured and design. Next up, we have clock tree synthesis. Now, all chips, or all digital chips, are going to take an input clock at a certain frequency that needs to be then routed efficiently to everywhere it's needed on the chip. And this is what clock tree synthesis does. The idea is basically that we want to connect up this clock signal to everywhere it's needed in the chip while minimizing skew, jitter, and power consumption. You can see, firstly, jitter here. Jitter is when we get these sort of like up and down, really fast, bouncy type signals that we don't want. And then you can also see we have skew. So skew is basically the difference between the time that a signal should arrive and the time that it actually arrives. And if the skew is too high, this can be very detrimental to the overall functioning of the chip. Next up, we're into sort of now the physical characterization section. So essentially our chip is laid out now, it's done, but we've only completed like maybe half or like a quarter of the battle, because now we need to understand how this chip is actually going to perform in reality. And so, this is very important, probably arguably one of the most important parts of the design pipeline. And timing as well is particularly important because it tells us if our chip placement that we just performed is actually acceptable or not. And we can perform timing analysis using a technique known as static timing analysis. And this can actually provide us with a very accurate estimate of the timing of the chip. It will determine basically if we have what's known as positive or negative slack. And negative slack is bad and indicates a timing violation. Basically, data arrives after it's sampled, which is very bad, so we can't have that on a manufactured chip. And positive slack is generally good, but we don't want too much positive slack. Ideally, we want our slack to be around about 0, which means that the layout is about as efficient as it can be. Now, OpenRoad has an open source timing tool called OpenSTA, which is a gate level STA tool, which means that it models resistors, capacitors, and all of that stuff. And on the right-hand side here, you can see an actual timing report that I did with OpenSTA for a real chip, and I think it's good. I can't remember. Anyway, so the next thing that we've done now, assuming we've figured out that our timing is acceptable, we now need to consider power and thermals. So as I'm sure you all know, chips get very hot. Just ask NVIDIA about their graphics cards. Heat is, of course, a byproduct of transistors switching, and hence power and heat increases as the switching speed increases. So once we reach these gigahertz speeds, it becomes a real issue that we need to consider. We need to understand the way that the power is drawn and the heat is generated if we want to actually make use of this chip and integrate it into a real product. Now, OpenRoad has a IR or power drop analyzer built into it, which is what generated the diagram on the right here. This is for a small RISC-V CPU. But there's more powerful commercial options. The open source, this is one area where the open source options aren't actually that good for now. But again, this is sort of just a bird's eye view. There is much more to physical characterization that I haven't gone into, including parasitic capacitance extraction, which is used if you want to model the chip at a very, very fine-grained level, analyzing voltages on the chip, antenna analysis, because actually the traces on a chip can get so long that it will act like a radio antenna, which you definitely don't want. Packaging, there's a whole different field about packaging it into the epoxy sort of plastic box that you get. Electromagnetics is increasingly becoming a more particular issue, and there's many, many other things. This is one of the hardest parts of chip design to get right. And remember, an ASIC tape out can cost millions of dollars. So it's also very important to get right. You don't want to have to respin a chip, because it is possible that if you end up needing to respin a design, the entire company will just go bankrupt. So let's assume everything worked out great and we're now ready to export our chip. We can basically export what's known as the photolithography mask, which will be sent directly off to the foundry and etched onto a wafer to form the final chip. This is usually in a file format called GDS2, but nowadays Oasis is sometimes used. And this is sort of like a G-code type file format that actually describes the graphics of the chip. These designs can also be viewed and edited in FOSS layout tools like K-Layout and Magic. And in fact, you can actually skip the entire design pipeline and just draw the chip up yourself in K-Layout for small chips. You probably wouldn't want to do that for big chips. And at this stage, we also want to apply design rule checks, or DRCs, to ensure that our design is going to be accepted by the foundry. If you've ever done PCB design, this is very similar. You apply the DRC checks before you send it off to PCBWay or something like that. And the final thing we want to do is do some verification. We perform what's known as layout versus schematic, or LVS, to prove that the finalized chip is equivalent to its original design. So basically, we can prove that the tape-out process hasn't, or more so the place-and-route process, hasn't introduced any changes to the chip that we don't want. So, all right, the info dump is over. To recap the final stages, we went through floor planning, placement, routing, clock tree synthesis, physical characterization, design rule checks, and the actual mask export. But still, this is a bird's eye view. We didn't really cover each algorithm in detail. You probably need an individual talk for each algorithm. Some researchers will dedicate their entire academic careers just to research one particular algorithm here. So, any questions before I go to the final section? Yes? The layers? Yeah, so each foundry will generally have a different, what's called layer stack up. And there are each foundry will have a certain number of, say, metal layers and copper layers, some of which are used as interconnect, some of which are used for the actual transistors. And sort of, I guess, similar to PCBs, the more layers you have, the more flexibility you have with routing, because you can route things, under. And yeah, so it depends a lot on the foundry, but the tools will all consider that as part of the design pipeline.
Another question. Do you use place and route tools to facilitate like signals and everything to it? Because I'm not sure. It seems like everything is on such a small scale compared to PCB. If these are bare silicon traces, so to speak, is there anything that it takes account, for example, with one clock line later and another one?
Yeah, it's definitely true. It's a bit, this is one of the reasons why I think auto routing PCBs is difficult, because with actual PCBs, you can have very high voltage currents that are traveling next to each other, and you have to, consider, signal integrity. Because at the ASIC level, things are so minute, And also the voltages are very low, typically say 0.5 to 1 volt for modern chips. The signal, the actual sort of like EMI stuff is less of an issue, but what is important, very important, is the way that clocks are done. So things like clock domain crossing, where you have a clock go from one domain to another, is very bad. And of course, obviously, you need to minimize skew and jitter that we talked about in timing analysis. So the routing algorithms will have an estimate of the skew and jitter as part of their objective function, and they'll be able to help to minimize that. But a lot of the time that you spend in the design pipeline is going to be tweaking parameters and tweaking design parameters to meet what's called time enclosure. You want your chip to run at 1 gigahertz, you have to make sure that you can actually run it safely and assuredly at that. And also, as well, I skimmed over it a little bit, but of course the antenna analysis as well is very important because, yeah, these long traces on your ASIC can actually turn into antennas and, pick up background noise, and it's not good. So, yeah. Cool. All right. Well, I will get into the final section, which is sort of a bit of my advice about if you're interested in this stuff, how you might be able to get involved. So I thought I'd share my personal journey, how I got here. I started programming in circa 2013 at probably about 10 due to Minecraft. I wanted to make Minecraft mods. I was initially interested in game development throughout school. I thought C and C++ were scary. I didn't want to touch them. But I finally got interested in embedded C programming through my school's Robocop Junior program circa 2019. And after taking CSC 2010, I was already a little bit interested in chips, but after doing that course, I really wanted to get more into chips about 2021. And I, of course, bought the book, tried to hoover up all the information on semiconductors that I could. I learned System Verilog in about 2022. And finally, I was able to do my thesis as well on electronic design automation, and that taught me a huge amount as well. And of course, in the future, I'm planning to do a PhD at Macquarie's Silicon Platforms Lab, which will, I'm sure, teach me much, much more. So that's my journey. But my disclaimer is that this is all my personal advice about how to get involved. I learned in a non-standard way, and so what I will propose is very different to how most academics or instructors will advise you to learn IC design. So take it as you will. If you want to do chip design, the best way I think to get involved in Australia right now is to just be passionate about it, read lots, and work on it in your spare time. The reason being is that Australia doesn't really do chip design. If you're going to specialize in it, be warned that you are specializing in a very challenging area that this country unfortunately doesn't really care to invest in yet. But I would say don't let this stop you, because as we know, I covered in the introduction, chips are very important. They underpin everything. They're a geopolitical issue, and times are changing slowly. The Silicon Platforms Lab that I'm applying to didn't even exist 2 years ago, and now it's here. I don't know what the best way, I can't advise you on the best way to get involved in. I'm of course doing a PhD, but industry such as AMD and Blackmagic could be an option for high achievers. I'm sure the interview process will be quite challenging, but there are some semiconductor companies in Australia. If you are interested in this type of stuff, please feel free to talk to me afterwards. I think collaboration, since this is such a small area, is very important in this sector. However, if you want to do FPGA design, there's more good news. It's much better than chip design in Australia. Yes, it is true, and one of the reasons I think many people have heard about FPGAs is because it's commonly done at high-frequency trading companies. It is true that HFT companies do FPGAs, and it is true that they pay a lot, but these jobs are very rare and also very highly competitive. Most people probably are not going to make $1 million doing FPGA. Usually hardware is actually generally paid less than software. But if you're interested in FPGAs for the sake of them being FPGAs, the good news is that there's many other alternative options for you. There's options around UQ. I did hear recently that UQ's quantum and possibly optics departments were looking for FPGA programmers. There's options in aerospace and defense, energy, high performance computing, robotics, and many, many more areas. There's basically FPGAs everywhere. You're very surprised when you see them, but they pop up all the time. It is challenging work, but it is relatively employable, as much as anything can be employable in this economy. So the other option is, can you do anything at uni? Kind of. CSE 2010, I did talk about it a lot. It's kind of a must. If you haven't done it already, you really should. It's a great introduction to digital logic, and it's run very well. If you're interested in the EDA algorithms themselves, I recommend Comp 3506 algorithms and data structures, Comp 4403 compilers and interpreters, COS 2500 numerical methods, COS 3500 high performance computing. I haven't taken it, but I've heard Math 3202 is good. That's operations research that'll teach you more about optimization. And also Comp 4500 if you're interested in maybe understanding more about this sort of big O notation, like, NP complete and that type of stuff. If you're interested in the FPGAs themselves, there is CSSE 4010, but it is more, I've done it, and it's more MATLAB based and focuses much more on digital signal processing, like kind of how you can use the FPGAs to do signal processing. You'll probably spend a lot of time in MATLAB and in Simulink. So basically my takeaway is uni doesn't teach you everything, you just have to do a lot in your spare time. So what can you do in your spare time? I think you should start with FPGAs and work with open source tools. This is where me and sort of professors will differ, because usually professors want you to use Xilinx and proprietary tools. I started with open source tools because I didn't have access to proprietary tools, and that's how I learned. If you don't already have a Linux box, set yourself one up, and you can install UQCS. They have a Tabby CAD suite, which you can install very quickly, or you can also get UQCS from any other source you want. I do still highly recommend reading Digital Design and Computer Architecture. That book will take you from sort of knowing nothing about digital design all the way up to designing your own RISC-V microcontroller from scratch, which is very cool. Learn System Verilog. I recommend System Verilog or Verilog. You can learn VHDL if you really want to. It is done in CSSE 4010. I would also recommend buying a cheap FPGA board that's compatible with UQCS or NextPNR, and NextPNR. The one that I used was the Orange Crab 85K, which is a lattice device. I put cheap in quotes because it's not really. I recommend splitting the cost amongst your friends. I did that, and you can sort of just like have it on loan with a couple of weeks. Design some basic circuits that solve problems you're interested in. I designed circuits for Robocop Jr. To sample light sensor rings and stuff like that, and that was a great way that I learned a lot about System Verilog. The other thing as well is you really want to simulate and verify very intently. In industry and in academia, they care a lot about verification. So open source tools that are good for that are GTK Wave and Surfer. These let you see sort of the timing of your circuit. You can see the little waveforms. And the simulators that you should use are either one of Icarus Verilog or Verilator. They're both good open source simulation tools. And finally, I do advise, if you're interested in this stuff, reading the code of the tools you use. This is the beauty of open source. You can dive into it. I've read a lot of the code for UQCS. I've worked with it, and I've read a lot of open road code as well. So, it's good to take advantage of that as an open source tool. Finally, these are my references, and that's about it. Thank you so much. If you want to read my blog, shameless plug, the UQCS blog, and yeah. Any questions, I guess? Yeah.
So from what I got from this talk, one of the things that you discussed is about like digital design.
Yeah.
But if you're interested, like, what should you do if you're interested in more like mixed